No way.
And I'm very pleased to introduce Leonardo Pacheco, who will speak on determinacy and reflection principles in second-order arithmetic.
Yeah, so good morning. I'm presenting this with Keita. Keita should be on Zoom. You can see him a little small there, but he can talk. So today I'm going to present a result that we are finishing right now, relating a determinacy and some kind of reflection principles. First, okay, this slide is a little ugly. We get this kind of reflection for some kind of formula for some system. It's going to be equivalent to a determinacy for finite differences of sigma 01 or sigma 02 or sigma 03 sets. I'll revise the definitions later. For determinacy, we use lots of things that Montalban said yesterday, but the notation is all different, so I need to go over it. And like the third item was the first that was obtained. It is a result by Lejek in the paper, but it used a quite a result of quite a long proof, quite as long as a PhD thesis long proof, and it had a quite strong basically used by 123 as basic systems. So we got it better and we generalized it for other settings. So what is determinacy we're thinking of? Just determinacy for the Gale-Stewart games. We have players building infinite sequences of natural numbers, and we have a payoff. Here we're gonna consider payoffs both in the pair space, so the players can choose any natural numbers, and Cantor space, so only 0 and 1. Because of at the lower levels of determinacies, you have a difference there. Morris notation, we have that this gamma determinacy is going to be determinacy for games in gamma in the bare space, and if you put an asterisk, it's going to be determinacy for the Cantor space. So, okay, we're going to think about the difference hierarchy. The idea is the same as Montalban said yesterday. We're going to think of mostly Boolean combinations of sigma 01 sets or sigma 02 sets. As we want to put the for all inside the determinants axiom, we have to formalize the definition. So it gets a little bit more ugly, but what is going to really matter for us is for this you can get sigma 0k x is going to be the difference of x sigma 0k sets, and this x can be, well, depending on the model, it's going to be non-standard. So it's going to be finite inside the model, but it's bigger than we could get before. And we'll call the important axioms that this for all n sigma 0k and determinacy is like for all natural numbers, even non-standard, the difference of sigma 0k sets is going to be determined. Yeah, some player is going to have a strategy, and this n can be non-standard, and you just get all the Boolean differences, Boolean combinations of these sets.
But you're looking at finite level, so that you can try.
Yeah, finite
in a non-standard model.
Yeah. We get for the non-standard, we get a little
finite part of a different size.
Yeah. It's not omega. You can get infinite differences. So, okay, for the presenting some existing results on determinacy, we have that for finite, standard finite, differences of open sets in the Cantor space are going to be equivalent to ACA. This is a mistype, it should be weaker. Difference of open sets in the bare space is going to be equivalent to pi 1 CA, and for sigma 02 sets, it's going to be equivalent to multiple sigma 1 inductive definitions. I'll get to this definition later when we need it. This is just for the finite set. So for difference of 2, 3, 4, 5, and standard n, you're gonna get to things like 2 in the big 5, 1 not in the big 5. But if you put the quantifier, it's gonna be a little bit over. So you get that for all different finite differences of open sets in the Cantor space is gonna be equivalent to ACA prime. So you can take unbounded many Turing jumps or things like that, and it should hold. You do get the same for open sets and Pi11CA, that you get a Pi11CA prime. I don't know if this is anywhere in the literature, but the names and the same idea. So you can get unbounded sequences of beta models, or you can take the hyperjump as many times you want, even consider many times. And you also, and similarly, you get equivalence between the sigma 02 sets and sigma 11 inductive definitions with the for all inside the axioms. These three results, they kind of follow from these three, but as far as me and Keita are aware, they're not written anywhere. So the proof is not really new, but it's, if anyone knows where, if there's any place this is written, please teach me. I would be happy. And okay, why? And at last, mostly using a result of Nemoto et al., we get that the determinacy for differences of sigma 02 sets in the Cantor space and in the Baire space are going to have the same strength. If you look at the finite levels, it's going to have like a one-step difference, but if you put the for all quantifier, it's going to be the same in the end. And we don't need to look at the Cantor space for things greater and bigger than sigma 02. It just matters for the open sets. So, okay, we're gonna use these results later. So, okay, that was the determinacy results. So what are we gonna call reflection principles here? It's gonna be something like you get some finitely axiomatizable theory, you let PR be a standard probability predicate for it, and TR pi1 be a truth predicate for its pi1n sentences. So you get that pi1n reflection for T is the sentence for all pi1n formula. If it's provable, then it's true. And here in this formula, we kind of accept the parameters hidden in it because it's a coded formula. So you can have like non-standard natural numbers inside the formulas depending on the model. So provable, something provable somewhere, then it's true. You can relate it to the uniform reflection principle schema. If you get reflect for each standard formula, you can have reflection for it with parameters. It's gonna be the same thing in the end. If you try to prove it, just comes the result. It's not too much. So if you prefer to think about this kind of schemas, it's okay. But for the proofs that principle, yeah.
Sorry, maybe it's obvious, but why are you interested in pi1n reflection in particular?
Pi1n, we're mostly interested in pi13 reflection, but for one case in particular, we need pi12. Because difference of open sets in the Cantor space is going to determinants for it is going to be pi12, equivalent to ACA prime. So we need to define for n, but 2 and 3. So okay, and for some basic definitions, let us slightly review strong dependent choices. So okay, strong dependent choices, you get for some sigma 1k formula, you get some set that for OM and all set. If you can get the beginning of the dependent choices, you can extend it and the set is going to be fine. What matters for us is, first, it's convenient because strong sigma 1k choices are going to prove pi1k CA and sigma 1k dependent choices. And it is also conservative over pi 1k plus strong sigma 1k plus 3 dependent choice is going to be equivalent to pi 13k plus 3 CA over pi conforms is equivalent conservative. The more useful for us will be here. So we want to think of coded beta K models done. Also, again, mostly coded beta model, coded beta 2 models for our results. Coded beta model is just going to be a set of the natural numbers, and you get the slices of it are going to be a set, and they satisfy the same by 1K sentences as the ground model. So it's just a coding of its standard, so it should be fine. And we have that Pi1 CA is going to be equivalent to strong 1K dependent choices, and the existence of coded beta models, including any set, any given set. And the same holds for the strong models, Pi1 to CA, and dependent choices for sigma 1 2 formulas, and the equivalence between existence of coded beta 2 models. And if you go above, it just holds for sigma 1, dependent choices and beta k models. But with v equal to L, you get also the equivalence with Pi1 KCA. Again, we're kind of defining in general, but we're just gonna use a few lower instances. So what are we using the beta models for? We're gonna prove those those results connecting a reflection and determinacy using this kind of sequence of beta k models. So we get this kind of ugly formula, psi IE of n. It's gonna state that we get a sequence of beta I models, y0, y1, y2, until yn, I for internal, so it's a relation between them. And the last one is going to be a beta E model of a coded beta E submodel of the ground model. And we usually taking this last relation, the beta E, to the E be smaller than I for convenience on the proof. And for each E, this is going to be a pi E plus U formula, and we get this kind of ugly theorem that we're going to just use a few pre-instances of them. So for all n, psi I E n is going to be equivalent to pi 1 E plus U reflection for a strong sigma 1 IDC. So let's take a look at the proof for this. First, for the easy half, from reflection to the for all n psi n, for our results, we use proofs like this. Many times the proof is always the same, and it's kind of boring, but it works. So you have, with strong dependent choices, you can say you have a really small sequence of beta models like 0, and you can formalize it, and I don't know, HA0, and it should be fine. And you also can formalize that if you have a sentence of size n, then you can extend it by 1. And now we formalize it. We do induction by the end here because of this probability of something. It's gonna be exists the proof, so it's a sigma 0, 1, and you can use sigma 0, 1 induction, kind of hidden to get that this probability holds for psi I n for each natural number n. And then for reflection for each n, you get a psi I is gonna hold. And as you got it for each n, you can put it for all quantifier and holds everywhere. And yes.
So just to be sure, just clarification, n is the length of the sequence of the beta model.
Yeah, it's the length. I is the I of the beta, I of inside, and it's the same. So you're kind of, it should be a little stronger if it is a sigma 1 thing. And for most of all of the results we have from reflection to something are gonna be like this, so we don't put it anymore. For the other way, we got a little more interesting proof. So let's say we can get sequences of beta E models of any length that we want. We're gonna think of a theory, first order theory, and get a model for useful model for it, which is gonna give us a contradiction. So let's say you can prove let us abstract a little the indices, it's gonna work, but so you have strong dependent choices and you can prove for all x, theta x on it, but it's not true. Then you get some x0 that is gonna make it hold. We build this first order theory that we have that the first order part is gonna be a discretely ordered semi-ring. Each of the, we build a M coded models over this thing, and each model, coded model, will satisfy HA0. The models will be beta isomodels of each other. And then a little tricky part is that we want the each coded model in the sentence we have in this model, it's going to be a beta ISA model enough. We can do a beta ISA model because the first order part may be non-standard inside the model we're thinking of. So we just get it beta model enough because if you have a weakness for a formula outside, then you can find a weakness for a formula inside. But the converse may not hold, but we don't need it for the proof. And we have x0b inside the smallest of the models. So okay, this is going to be consistent as we can get arbitrary long sequences of beta models, and so we get a model for it. First thing, this model is going to be a model of dependent choices because for strong sigma y dependent choices, because you can get it increasing, the hyperjumps inside it, and it is going to satisfy a theta for x0 because any model of dependent choice is going to satisfy it. But you can use a beta ISA model enough to push inside the negation that you have inside the model, and you get a contradiction. And so you can prove this reflection from the arbitrary long sequences of beta models. So, okay, this is I don't know what this means. Let's get to a little more concrete things. Let's think E and I equal to 1. So you get arbitrary long sequences of beta models, coded beta models, and this is going to be equivalent to a pi13 reflection for a strong sigma 1 dependent choices, which is equivalent to pi1 CA, and this arbitrary long sequences of beta models is going to be, well, it's the same as saying arbitrary long hyperjumps, and we had before that this is going to be equivalent to the difference of open sets on the pair space. Okay, so this you get one of the results. For the open sets, we can do something in Cantor space. We can do something similar, adapting the proof that we had of infinitely long beta models for something like infinite long sequences of Turing jumps. And we get that the HA prime is going to be equivalent to the pi12 reflection for HA0. The proof works like that, but the way we build the models is a little different. And we use the results that we already have from Determinacy to connect it to connect this here, and we got equivalence. So, okay, the results that go really easily are these two, and so now we want to think of the sigma 02 sets on the pair space. Difference of sigma 02 sets on the pair space. Okay, for this we need a little bit more of work. It just doesn't go smooth. So from reflection to determinacy, the proof is straight. From determinacy, we get a result by Metzala and Tanaka that it's going to be equivalent. And we just proved the connection between reflection and sequence of beta 2 models. And we're going to use multiple inductions to create sequences of beta 2 models. So I'll restate this later with the pretty system names. So okay, what is the sigma 1 inductive definition? You get, so now, you have an operator from the power set of n to the power set of n, that is defined by a sigma 1 formula, and we're gonna define this. Gamma prime x is gonna be gamma x unit of x, and the set inductive definition defined by this operator is gonna be this fixed point of this gamma prime. So you start with the empty set, you apply gamma once, and then you apply it again to what you get, and you put everything together, apply gamma, put everything together, apply gamma, and so on and so on and so on and so on and so on, which may be quite long and so on, but. And we want to do it with for many inductive operators. So we get it for multiple inductive definitions. You get k many sigma 1 inductive operators, and you do the same to get the fixed point. So you get the first one, then repeat it until you get a fixed point, apply the second one once, and then go back to the one, and go so on. It gets kind of ugly, but the important part for us is that if we get this inductive definable set, is going to be simultaneously the least simultaneous fixed point of all the k operators that we have. So we just the precise definition here, you kind of have the structure of the points, the fixed points you build, but we don't need it here. We're just gonna use the fixed point the least fixed point of all these operators. So, okay, we're gonna now try to think of some operators that we can use to make the synthesis. We're not completely just gonna prove sketch the idea for creating the sequence of just two models, because it's uniform to go the whole way. And okay, you wanna make that M0 and M1 are better models of the ground model. This is fine. You wanna make M0 be a better chosen model of M1. This is also kind of fine. But making M0 be an element of M1 and kind of guarantee that they grow, it's gonna take a little more work. So we're not just gonna define the coded models at once. We're also gonna define a few auxiliary sets. So you have the models, M0, M1. You're gonna have a set of recipes for the sets inside the models. We're just gonna be our instructions. So you build this from this using this. You'll get to the recipes later. And you have to save a copy of the smaller set that you want to put inside the bigger coded model. So let's slowly take a look at the sequences, the recipes that we have to build. So first, we're gonna use three operators, gamma 0, gamma 1, and gamma 2. Gamma 0, it's first gonna make me have a closure on the by one comprehension. So the models are better models of the ground model. So if you have any set that's already made and it's not empty and you have a description for it, then you can make the comprehension for the if pi set, pi one set with using j, this set that we had already made, j as a parameter. So this is each time we take it, we're gonna repeat it omega many times to get to the closure under pi 1 comprehension. We also get gamma 1 that is gonna make the two models be a better chosen model of the other, which you kind of take a look at some formula that you have someone exists for all theta, that there's someone in the bigger one that satisfies it, and there's no one on the smallest one that doesn't satisfy, and you just take a weakness on the right part and copy to the other one. Usually you just take the smallest recipe, so you can just copy it later. And the little more confusing one is putting M0 inside of M1. So if you have the current copy you had of the model, and the model you have right now that's going to be a little bigger, you're gonna have some recipe that is different, and you take it to a witness and save it for saying the next time you build the recipe, you make the recipes, you can copy the candidate you have. And also you store the M0 you have as a copy. And yeah, you have that it's different, then you're gonna have a way to say it's different, a witness. Just matter that it's a witness, doesn't matter the details. And you copy it. So you get this kind of recipes, you get a witness to say you increased your model, the smallest model, and then you have to copy it again. So, and also Gamma 0 is gonna make the recipes. So you have a description for comprehension, you can just build it. You have a description to copy a set, you just put it into the set. So we can also make the recipes so that you just make them once. And you have to copy this, then you get the copy you had and put it inside them more. So you got this Gamma 0 making the two models being better models, Gamma 1 making the one model being a coded model being a better chosen model of the other, and Gamma 2 makes the smallest one be an element of the bigger one. And for ON, you just increase the sets of recipes and the copies that you have for the smaller ones, and the proof goes through. So you get that for using any some f of n many inductive definitions, then you can build arbitrarily long sequences of better models. There are two models inside, better model outside. And we already had the connection with reflection, and so reflection is going to be equivalent to determinacy here. So, I'm speaking fast. Fine. For the last result, these were still using a Montalban and Shor's result. So we had this yesterday that from comprehension, we can prove the difference, determinacy for differences of pi03 sets. And from determinacy, you can get the existence of better models of a simpler comprehension for that 1M set. And now we have these results. We formalize them inside it. Well, HA0, and we get that for OM, the pi 1 m plus 2 CA0 is going to prove the difference of M sigma 03 sets. And similarly, we get that for OM, the determinacy of the difference of M many pi 03 sets is going to prove the existence of beta models of delta 1 m plus 2 CA0. And we can use this to prove that, connect that. For all sigma 03, determinacy is going to be equivalent to pi 13 reflection for Z2. The reflection, from reflection to determinacy, it's straight, like before. For the other way, we're going to suppose a reflection doesn't work. So you can prove it, but it isn't true on the ground model. And then you use this corollary so it's provable on Z2, then it's provable with some kind of a pi 1m comprehension for some n, and you fix this n, and you build a better model for something greater than it, but then you have that the formulas that doesn't hold outside holds inside, but as is the better model, we can push that formula that doesn't hold outside also inside the model, and you get a contradiction in that inside there. So, okay, you have reflection. If it's provable, then it needs to be true. And the current proof is still just formalizing a Montalban chart. And that's it. I think I spoke a little too fast, maybe. So, Mallory, the reference.
Yeah, thank you. Since his project is a bit faster than I expected, so could I just say a few words about? I mean, could I just summarize the idea of the talk, perhaps?
Pleased to introduce Keita. I wish you were here, Keita. Please go ahead.
Oh, yeah, thank you. So, Leonardo, could you show the second slide? I mean the part of the main theorem.
I'll get there someday. But
Well, no, the first one. Yeah, yes, that one. So okay, so I think the idea of this research is that so as yesterday's Antonio's talk, we have already, in some sense, we have already know that the determinacy principle itself is usually just like a pi1-3 version of something. And indeed, very often it characterizes some pi1-3 part of some stronger axiom. That's the known situation. So, and we want to reformulate or rephrase that situation using the using more like a syntactic deflection principle. I mean, so it's kind of all these results are, I mean, almost expected, and well, perhaps might be folklore for some of you, perhaps, I'm afraid, but anyway, we'll try to rephrase the determinacy in terms of reflection. That's the original idea. So what we want to say is, okay, well, determinacy is always something like pi1-3 reflection of something. That's the basic idea. And for that, okay, we have already know several versions of like pi1-3 conservation between comprehension versus determinacy. So to formalize that idea with the terminology of reflection, we need some good characterization of reflection. And that's the one provided in the, sequence provided by the sequence of beta models properly. Can you change the slides to that page, Leonardo?
this one?
Yes, yeah. So this is the, I mean, it's actually quite simple idea and nothing difficult to prove. I mean, using just basic Bauer-Schripp style argument, but this characterization provides us just to show deflection. Well, okay, we can just consider more like a model theoretic way, just constructing a long enough sequence of beta models. Then we can imply the reflection. That's the idea. And constructing long enough beta models, it's very, very much, I mean, much easier to induce from determinacy. I mean, determinacy is often used in that way anyway. So that's another idea. And combining those, we can rephrase, well, determinacy by reflection. So that's the very basic idea of the talk. Well, thank you. I mean, just a summary of the talk.
Thanks, Keita. Questions for Leonardo and or Keita?
Your inductive definitions were non-monotone, right? You were working with non-monotone inductive.
Non-monotone. For this case, it's equivalent.
When you write,
Yeah, it doesn't. For this case, it doesn't matter if it's non-monotone or not.
Okay.
There's going to be a question from.
Yeah, I see. Harvey, you have your hand up.
They need to promote him a bit.
Oh, yeah, I think somebody has to activate your microphone.
Yeah, I've done that.
Or else working.
Oh, okay. No, Dennis has done it. So.
Hello.
Yeah, go ahead.
My question is, most of you expect this question. What about Turing degree determinacy? And let me tell you, I asked this question because although the formal statement of Turing degree determinacy is not terribly philosophical, it is in fact related to a lot of philosophy that I'd like to one day pin down. So let me just ask you Turing degree determinacy.
Sorry, can you clarify for me what is third degree determinacy? Are we talking about
Martin's cone theorem for,
Yeah, probably I would answer. I mean, so
go ahead.
we haven't studied yet. I mean, quite reasonable question. It sounds very good, but just we haven't studied, so we don't know. I mean, but yeah, you're right. I mean, it is expected that the Turing determinacy could be rephrased by some deflection or those kind of terminology. I agree, totally agree. But just we haven't studied yet. Good thing for the future work, probably. Thank you.
Yeah, I mean, it's usually pretty robust. I didn't push Antonio about this because if you change the notion of degree, even a little bit at least, by requiring the reducibility to be much stronger or even much weaker, it seems to be pretty robust when you are at least robust when you're talking about pretty reasonable sets, applying it, in a certain at a certain level, in the Brell hierarchy set. So it's pretty robust, and I want to make a big fuss about it because I don't usually ask technical questions that much, and it sounds technical. But I think that and Antonio said that that they did work that out, it was required different methods and somewhat different methods, and it was well worth it.
Yeah, thank you. Yeah, we should think about it. Thank you.
Any more questions? Here, online. Okay, thank you so much, Leonardo.